Marco. Marco, do you want to ask your question yourself? Okay, I can also read it out. So the question was, what properties does the water inside the Kamiokande experiment has to fulfill?
Oh, I don't know. Ultra pure it has to be to avoid scattering. Oh, okay, sorry. I think there's someone much more expert than me. Can you answer?
So it used to be ultra pure, which is quite, I mean, it's got bacteria that can be found in people's armpits from people falling into the water. But yeah, usually ultra pure, and now it's got delinium loaded, so we can do some like nuclear recoil measurements and stuff. So, yeah.
Thank you.
Okay, I hope, Marco, that answered your question. Okay, thanks. Yeah. Then if there are no further question, we can maybe continue. And I think so the speaker is still not working, right? I don't know. It's not okay. So it's working on my iPad. Oh, you have questions?
So the upper limit in energies for the cosmic rays around 10 to the 20 eV, and I think that's because of the GZK cutoff, where we have the delta baryon resonance.
Yeah.
So we also see gamma rays near the sources and protons, right? So is there some kind of a resonance that could happen near the source, which could actually lead to that cutoff, or is it only due to delta baryons?
Well, there is no way to avoid the baryon, the resonance during the propagation of the cosmic rays. But if the energies that got accelerated initially were not high enough, so if my source produced 10 to the 20 electron volts, so anything could happen inside the source, but if the source, the cosmic rays escape the source with 10 to the 20 electron volts, they have no choice but to interact on their way. The only thing that could be the case is that what we observe in the spectrum is not the GZK effect, but rather either for reasons of interactions inside the source or just that the acceleration is not efficient enough. We never accelerated these 10 to the 20 electron volt cosmic rays to begin with. So what we see is a cutoff which has to do with interactions in the sources or acceleration limited maximum energy. You look unconvinced. Oh,
I mean, so we are not entirely confident why it happens.
Exactly. Yeah.
It could happen near the source, or it could happen in midway while coming to the Earth.
What we currently observe is consistent with both scenarios.
No.
It could be, but it's not precisely the GZK, so people are speculating that something is inside the source or, yeah.
Thank you.
Okay, I think we should continue.
Okay, yes. So since we've started talking about ultra high energy cosmic rays, that's the next thing I'd like to talk about today. And it's going to be quite a lot more focused than the previous things we discussed. So please bear with me and ask questions to make sure you are with me on this one. So let's see if I can. So here, I wanted to remind you, or those of you who have already seen this plot, that the cosmic, this is the, okay, I think it's better if I, so the cosmic ray spectrum we observe extends out to this 10 to 20 electron volt energy. Up here we have galactic cosmic rays, and this is the what I called before, the very likely extragalactic component. And we saw that there is this interaction whereby cosmic rays lose a significant amount of energy, and as a result, they produce neutrinos. And so 10 to the 20 electron volt cosmic rays, a 20th of that energy is about 5 times 10 to the 18 electron volts. So they produce 5 times 10 to the 18 electron volt neutrinos. Such neutrinos we haven't detected yet. IceCube has detected neutrinos with energy up to 10 PeV. But there is a possibility that all cosmic rays from 10 to the 18 up come from the same source class. Okay, we don't know. There might be one or more source classes. And so there is a possibility that these neutrinos come from the same sources as these cosmic rays, but it's also possible that there are two populations. And so this is sort of what this next topic I want to talk about addresses. So here, what is important is that in this plot, we have energy flux as a function of energy. And in these axes, in every decade in energy, we have the same energy content for an e⁻² power law in terms of numbers, dNdE. So this is E squared dNdE, and in this, this is so a straight line corresponds to an e⁻² power law in terms of the number, the number differential with energy, and therefore a straight line tells us that we have the same energy content per decade in energy. And so the fact is that the neutrinos seem to have essentially the same energy content per decade as these extragalactic cosmic rays before the cutoff really kills the flux. Okay, good. And also we have a possible connection to the gamma rays because of the neutral pions, but there are other ways to make gamma rays in addition to neutral pion decay. So this idea was there a long time. Okay, I think I already said what I wanted to say here, that maybe the sources of the ultra high energy cosmic rays are going to tell us the neutrino flux before there was IceCube to detect the high energy neutrino flux. And so we're going to go through this. This was done, you see here the reference in the 90s by these two people, Eli Waxman and John Bahcall. And we're going to do this calculation for ourselves in order to predict the neutrino flux that comes out of the observed cosmic ray flux. And these 10⁻20 electron volt cosmic rays were detected already 50 years ago. Okay, such a beautiful flux only became available in the 2000, or let's say when Auger started operating, so 15 years ago. But so people knew what the cosmic ray flux was like at this high energy, even in the 90s. So they were able to do this calculation. So, and I'm just indicating here with the dashed line where I'm going to normalize the cosmic ray flux, because you see it's a very steep cutoff. So if I were to take the flux here, I'd get a different result. But I'm assuming that there is some process here which I should ignore, and that the energy content produced by this population is given by the upper flux. All right. So what we want to do is calculate the production rate, the energy production rate of ultra high energy cosmic rays in the local universe. And so how are we going to do this? We need to know, first of all, the energy density of cosmic rays, which we're going to get from the cosmic ray spectrum. And second, we need to know what is our denominator, what is the volume that we need to divide the energy content by, because we want an emissivity. So an energy per unit time per unit volume. That's the emissivity of ultra high energy cosmic rays of the population we're searching for. So first, we're going to calculate the volume that over which we're seeing cosmic rays. And so cosmic rays lose energy via these interactions that we talked about before, photopion interactions. And the main way in which they lose energy is by interactions with the CMB. So here you see the different photon backgrounds in terms of energy. And you see them here again plotted as an E squared dNdE, so an energy flux. And you see that the CMB is the dominant in terms of its energy flux. There are other backgrounds like the infrared background, which is the light from all the stars. But the CMB dominates, and it also dominates in terms of number, which is actually what we're going to use for our calculation. So in order to know what is the energy loss length of these cosmic rays, first we need to define the mean free path of the cosmic rays. So the mean free path lambda is inversely proportional to the cross section. So the larger the cross section for the interaction, the smaller each step, and the number density of targets. Again, the more the targets, the smaller the mean free path. And from that, we can also go further and define a relative energy loss per unit time. And so this has, so this is the inverse of the mean free path. So the larger the mean free path, the larger the time until I lost my energy. And it also has we want to convert from an inverse length to an inverse time. So we have here one speed of light, and we also need the inelasticity of the process that we're losing energy by. So kappa, that's just delta E over E. And from this energy loss per unit time, we can also get the characteristic length over which my cosmic ray will have lost all its energy. So that's the inverse of that quantity times the speed of light. Now, in addition to the photopion process, which we already talked about, there's another process which is simple pair production. So the proton, which interacts with a high enough energy photon and produces a pair, an electron-positron pair. So this has a very small inelasticity because we only need to produce 2 electrons. So the inelasticity is of order 10 to the minus 3. And this is the cross-section here. And in order to calculate the mean free path, we need to know the number of CMB photons, which is this one here, 400 per cubic centimeter. And so putting these numbers into the mean free path expression, we get that the mean free path is about a megaparsec. And since the inelasticity is 10 to the minus 3, the horizon for these cosmic rays is about a gigaparsec. That's how long until they've lost most of their energy. And which cosmic rays does this happen to? So you just have to to do a simple center of mass energy calculation. And if we put here the energy of the photons in the peak of the CMB spectrum, we get that cosmic rays with energy exceeding 10 to the 19 electron volts will have this process. They will be affected by this, what we call the Bethe-Heitler process. And we have, so this is the one process, and you'll see that actually that's the one that's going to be an important process. We also have, above a certain energy, we have these photopion interactions that we already talked about. So in the, again, for CMB photons, the threshold is about 10 to the 20 electron volts. Here, the mean free path is very small. It's only 6 megaparsecs. And so in each interaction, the proton loses about 20% of its energy. So the loss length is also small. It's only 50 megaparsecs. So that's, I think many of you know this, but those of you who don't know this, ultra high energy cosmic rays tell us something about the very local universe, so 50 megaparsecs, and neutrinos tell us something about the entire universe because they don't interact. So for the non-astronomers, I have here, what are these distances about? So the nearest galaxies are about a megaparsec away. And if we have like a rare population, we're gonna talk about blazars later today. The nearest blazar is 100 megaparsecs away, just to give you a sense what these numbers mean. Yeah, so finally, we have energy losses because of the expansion of the universe. But actually this, so here, I'm just taking C over the Hubble constant for a very rough calculation. This has a larger loss length than the Bethe-Heitler process and of course the photopion process. So that's not going to be the most relevant one. This is the only one that affects neutrinos, right? Good, so this gives us our denominator, the horizon of the how long until the cosmic rays lose their energy. In other words, the cosmic rays that we see at the Earth, where have they come from? And now the energy density. So here is the plot of the cosmic ray spectrum that we saw before. And note the cosmic ray spectrum, every time you have to check very carefully what have they multiplied here by, because this is 2.5, okay? Before we had it to -2. And now I'm going to show you a standard plot by the Pierre Auger collaboration. This is this experiment that I mentioned in Argentina. that measured with a 3,000 square kilometer area. And now this is e to the minus e cubed. And why did they do that? Because they want to highlight the features around this region. Yes, also. Okay, this makes sense for an experimentalist, but we're gonna, yeah. But this is, I mean, this is what, good point, yeah. Okay, very good. So you have to always be aware of this when you look at cosmic ray spectra. So now we're gonna use this spectrum to calculate the energy density of ultra high energy cosmic rays. Okay, so here, okay, everybody calls this phi, but for the cosmic rays, we're gonna call it J, and then I'm gonna turn back to phi when I talk about the neutrinos. So J is just the differential flux. So this is number of cosmic rays per unit energy, per unit area, per unit time, and per unit solid angle. Okay, this here multiplied by E cubed. And now we want to find the energy density, so we just start from the definition. So the number density of particles differential in energy is just dn, dE, d unit volume, which is d cubed x here. And so I just split this into this volume element. I write it as dl times dA, so an area times a length. And there, this is a standard trick. And then since we're talking about relativistically moving particles, we can write this length that they've propagated over a certain time dt as c times dt. And the reason why we're doing this is to see that from the flux of cosmic rays, we can get their number density. So in fact, this form of writing it reveals that we have here J divided by C, and we're missing a d omega, right? So we actually, the number density is essentially the integral over solid angle. And since these are isotropically emitted particles, the integral just gives us a factor of 4 pi. So we can get the number density from the observed number flux with this 4 pi over C relation. And from the number density, if we do an integral in energy, we can get the energy density of ultra high energy cosmic rays. So we have energy times the differential number density integrated over energy, and that gives us this relation here, 4 pi over C times this integral over the number flux. So now I'm gonna do this integral very simply. So I read off here that we have, so I read off at this point that E cubed times J is equal to this. And therefore, and then I'm just integrating over 1 decade in energy very lazily. I take that the spectral index is e to the minus 2. It is not, but that just simplifies the integral. So the real index is 2.53. That's what they measured. But you see that actually we're going to get a pretty good value for this by this simple approximation. Just to, then we get log, natural log of E max over E min. And since we're integrating 1 decade in energy, that's just log 10 here. So we find out by just taking the number from the Auger publication that the cosmic ray energy density is about 10 to the minus 8 electron volts per cubic centimeter. And this is a good number if you know the energy density of the magnetic field. This is something you can compare to understand how important are these cosmic rays in the universe energetically. And now for the astronomers, we convert this to Gaussian units. So I don't know, for some of you, this might look alien. This is what I normally am used to looking at. So this 6 times 10 to the 53 ergs per cubic megaparsec. So 1 erg is roughly 1 tera electron volt. Okay. So the final thing we have to do, so we have an energy density, and we want to compare this to, so we want to get the emissivity of the population. So we want to divide by the loss length of the cosmic rays. And by doing this, we get the emissivity of the population, which is 2 times 10 to the 44 ergs per cubic megaparsec per year in my calculation. And any of you who study cosmic rays, can you notice any unjustified assumptions I've made here? Maybe Pablo. Yeah, I assume basically protons here. So this is, so for those of you who don't study cosmic rays, that's not very important, but it's a very important thing astrophysically that we now think that the cosmic rays that we observe are not just protons. So okay, I assume there are protons here, and then the UHECR collaboration has done this exercise much more properly with simulating the spectra of the cosmic rays at the source and simulating a mixed composition, not just protons, because they don't observe just protons, but they get the number, which is okay, a little bit different than mine. So it's about 5 times 10 to the 44 ergs per cubic megaparsec per year. That's the emissivity of the cosmic ray population of this spectrum that we observe. So back in the 90s, when Waxman and Bahcall this calculation, they also didn't know that the cosmic rays are not protons. They assumed that they're protons, and they derived that the energy production rate was 10 to the 44 ergs per cubic megaparsec per year. So for now, we're going to switch to their calculation, but you see it's only a factor of a few difference, and that has to do with all these assumptions about composition and the details of the shape of the spectrum. So now, if we have this population of cosmic rays, and we've seen the spectrum, we can calculate what is the associated neutrino flux, which comes from photopion interactions. So we need to make some assumptions here. First of all, we are assuming that the cosmic rays can escape. Now, I think I forgot your name, but you mentioned this scenario in which a lot of interactions happen to these cosmic rays in their source environment. So there it wouldn't work because we wouldn't see the cosmic rays. But if we assume that the cosmic rays can escape the sources, then we can get a benchmark flux or an upper limit to the neutrino flux from this population. And this is what we call the Waxman-Bahcall bound. So we are now going to basically do the inverse of the calculation we did before. So we have an emissivity here, energy per unit, volume per unit, time pumped into the universe. We want to know the time over which these neutrinos have been produced. So this is different than we had for the cosmic rays. Neutrinos don't interact. So we have here a Hubble. The loss length is essentially 1 Hubble volume. So we have here 1 Hubble time. Then, first of all, so in every photopion interaction, about half the time, the neutrinos that get produced are, the pions that get produced are neutral pions, so we don't get any neutrino. So we get a factor of 1/2 here. We get our C over 4 pi. This is what previously we multiplied by 4 pi over C. In order to go from emissivity to flux. And then we have another factor of 1/2, which corresponds to the fact that we're only interested in producing a single flavor flux here. And so half of the energy in every pion decay goes to muon or anti-muon neutrinos. So that's another factor of 1/2. And finally, we have something to correct. So the neutrinos span the entire Hubble volume. The cosmic rays span only the local volume, so that we have a normalization problem. We don't know how the cosmic ray emissivity is outside these 1 gigaparsec, but we can parameterize this and say, well, if the cosmic ray production rate was much larger in the early universe at large redshift, then this factor psi has to be something larger than 1. And vice versa, okay? If we have some sources that are only present locally, but we're not present at large redshift. So this is factor psi, which goes from point something to 10. And finally, we have to specify what fraction of the proton energy is lost to neutrinos. And when that factor is 1, we get our upper limit. So this is the calculation that was done in 1998, and they came up with this benchmark flux. This is the flux that they predicted for neutrinos from the sources of ultra high energy cosmic rays. And this is plotted here. So there is some uncertainty because of this redshift evolution that I mentioned. So not evolving sources, sources that do not exist in large numbers in the high early universe versus sources which were more numerous in the higher energy universe. And maybe you already know the answer here is where the actual ice cube neutrino flux sits. So very beautifully compatible with this Waxman-Bahcall benchmark flux. So obviously, okay, of those two, only one is alive. Well, John Bahcall is not alive anymore, but obviously they're very happy. And many other people find this very compelling that maybe we're seeing that with these neutrinos, we're seeing the sources of ultra high energy cosmic rays because of this coincidence of the ice cube neutrino flux with the prediction from the cosmic rays. Of course, it's still completely possible that this is pure coincidence. There exists another population, maybe it's cosmic ray dark, and or it doesn't reach extremely high energies, and it's contributing to the neutrino flux only. Okay, so this wraps up that part. Are there any
Can I
questions?
ask a question?
Yeah.
In the previous plot here, what's the OG 2016?
This is photon limits.
Photon limits. Okay.
Yeah,
Yeah.
I don't want to talk much about those, but they're quite excitingly good. Yeah.
Okay.
Yeah.
Thanks.
Maybe I can say something on Wednesday. Okay, anyway, so there is one final thing I want to say about the properties, the generic properties of this yet unknown neutrino population, which has to do with their number density. So again, this is quite specialized, but please try and stay with me. So I want to start by saying when we do an astronomical survey, we measure, I don't know, 100 galaxies out to some redshift. So we can work out by dividing the number of sources we measured by the volume out to which our survey was sensitive, we can get the number density of, let's say, normal galaxies. Of course, there is a problem that we don't detect the faintest of every population. So this statement only makes sense with that limitation in mind. Or if we can do some modeling and extrapolate and account for the faint sources. And here you see the number density of different source populations. So normal galaxies, there is about 10 to the minus 2 per cubic megaparsec, and then more and more rare sources all the way to 10 to the minus 9 for the rarest Blazars. So there's 1 per cubic megaparsec. So we can also write, we can say what is the volume within which I am expected to find one such source, and that's just 1 over the number density, right? So now in addition, we can do another calculation of the density, the luminosity density of the neutrino sources. And that's, to do it very simply, it's just to say that we have a fixed, all neutrino sources have a fixed luminosity L and some number density N. So if we multiply these two numbers, we get a sense of the luminosity density of neutrinos. And now we can rearrange this equation to get an expression for the distance at which I would expect to find the nearest source of a particular population of sources. So this, if the number density is just 4 pi times the number density over 3 all to the minus 1/3. So if the number density of my population is 10 to the minus 4 per cubic megaparsec, then I would expect the nearest source on average to be at 10 megaparsecs. Incidentally, this is roughly corresponds to the jetted AGN number density. And does anybody know the distance to the nearest jetted AGN? It's 4 megaparsecs. So it's not an exact calculation. So it's Centaurus A that I'm thinking of. Okay, so that's just an approximate, because of course the universe is not perfectly homogeneous on small scales. Now, in addition, we can say that the flux of any source with neutrino luminosity L at Earth is going to be 4 pi. So L divided by 4 pi times the distance to that source squared. And we can use this to say something else. So remember this plot I showed before? We can say, well, if IceCube didn't see any point source down to its limiting flux sensitivity, then and I specify the luminosity of my neutrino source, then I can say that that source cannot exist near the Earth. Otherwise, I should have detected it with IceCube. So I can get a sort of a lower limit to the distance of the nearest source if I specify the luminosity of my neutrino population. Okay. So this is it. So here I'm writing this F lim is just the limiting flux sensitivity of IceCube. So why am I doing this? So we have one expression for this distance, and we had another expression where we express the number, we express the distance to the nearest source in terms of the number density of the population. So putting these two expressions together, we can get a luminosity dependent upper limit to the number density of neutrino sources. And that is a limit which we can only place if we know the sensitivity of our detector. And that's a number that changes every day, because every day IceCube collects more and more data. And so we can only do this exercise if we say that IceCube has not detected any point sources. So now those of you who work in IceCube will have heard that there are some excesses and so on. So once we have discoveries, we are no longer in the business of making this limit. Okay, so this is only true if there are no discoveries. And so the bottom line here is that we can start to exclude some of these populations if we specify what is the neutrino luminosity of each individual source in this population. So here we have a plot of the number density of different source populations and the characteristic neutrino luminosity. Now, the number density is a fixed thing, it's something we measure. Of course, it has some limitations, like it comes from a specific survey. And the neutrino luminosity is completely unknown. But what we do know is that the product of the two for any population that explains the IceCube neutrino data has to be enough that we fit we get the entire IceCube flux. And that is shown here in this red band. So let's say I take non-jetted, or let's say I take low luminosity blazars, and I know that their number density is about, okay, actually this is not really, there is some detail here that has gone into making this plot that you don't need to know. But maybe let's say that their number density is 10 to the minus 8 per cubic megaparsec. And so they could be sitting anywhere on this line, their neutrino luminosity. But if it's sitting down here at 10 to the 41 ergs per second, then they simply wouldn't produce enough neutrinos to produce the entire neutrino flux. And if it's somewhere up here, then they would be overproducing the IceCube neutrino flux. Okay, so if we're anywhere on this line, we're overproducing the neutrinos, and if we're down here, we're underproducing them. So this calculation only makes sense if we demand that this population is responsible for the majority of the IceCube neutrinos. And so now we can superimpose this luminosity dependent upper limit, which we got before. And here it is. So we found out that that we cannot have extremely luminous sources of neutrinos nearby, because otherwise we would have seen point sources in the IceCube data. And so this gray region of parameter space is excluded. That is to say, all these populations which are very rare, like blazars, are cannot be the sources of all of the ice cube neutrinos because they are too rare and too luminous. And so as time passes, this limit is going to move in this direction. And we're going to exclude sources that are less and less rare if we don't see point sources. But now, of course, things change once we start to see point sources. So keep this in mind. And so this brings me to summarize this part. So what I've said so far is that, okay, neutrino sources the neutrino sources, whatever they are, they must be able to accelerate the neutrinos. We saw that quite a lot of populations seem okay in doing so. But they also must be able to account for this luminosity dependent upper limit constraint on the source number density. And here, sources which are very rare and powerful fail. And we also saw that in principle, the origin of the neutrinos can be the same as the origin of ultra high energy cosmic rays, because we worked out this Waxman-Bahcall flux and saw that the neutrinos fall in the same energy. They have the same normalization as that prediction, but this could also be a coincidence. So I'm going to switch to the next topic, unless you want to ask questions about this.
Wait a second.
So will you please elaborate about the jetted AGN?
Elaborate about
The jetted AGN.
the jetted AGN.
Yeah. How does it differ from the non-jetted one? And,
Yes,
yeah.
it's coming. Thanks for this question. That's what we're going to talk about next.
Any other questions?
Sorry, but where are the normal galaxies in the plot before? Because
good
they
question.
were
Yeah.
the denser one, no?
They're about here.
Ah, okay. So they are not excluded in general.
No,
Okay.
good question. Thank you.
Didn't make it on the plot, but yeah, not excluded. Any other questions? Maybe is there a question on Zoom?
There,
I don't see any. Ah, yeah.
Maybe you said this, but for the when you showed the plot of the Waxman-Bahcall bounds and then the ice cube flux, what redshift evolutions that correspond to? Does it correspond to a nice number, or
yeah,
does it
so
mean?
here I was showing a pessimistic and an optimistic, or rather, so here, this is a very positive. I don't know if it's the star formation rate. I don't remember if rapid evolution is probably more than the star formation rate. It's maybe like 1 plus z to the 5. And then that one is without.
Right, and then for the ice cube flux you showed on the next plot, was that able to be like does that correspond to an actual redshift value? Do they not? Okay.
That's just our measurement.
Okay.
We don't know. There are certain ways where you could, yeah, but we don't have any measurement yet.
Okay.
That can constrain this.
I have one question. Where are those neutrino produced? Where are those neutrino produced, which we calculate here?
These are photopion interactions in the source environment.
I saw it.
Yeah, but it just has to be not like a cosmic ray dart. So the optical depth is not 0, but it also shouldn't exceed 1. Okay.
Thank you.
Okay, yeah, there's a question in the back.
So the lower bound of when you had the number density and luminosity plot, the lower bound, is that assuming, have you basically like assumed that you basically go along and say one of those sources produces almost all of the neutrinos, or is that the minimal, like, is there also a minimal bound assuming that you just add them all up and it has to equal what you expect?
No, I am not aware of anybody who has done this calculation nicely for partial, because you see, so you're just gonna go below this line. It
Yeah.
might be here. So you are not gonna get us to the limit anymore. But so this,
the upper bound is like strong because there has to be, it can't, if it's over, then we can limit that. But the under, like the lower bound is based on your assumptions essentially.
yeah, so
Okay.
this bound only applies for sources that are dominant sources of the neutrinos.
Okay, thank you.
Okay. Another question. It's very good.
Imagine you now do this exercise with the proton-proton interactions. Would that be a subdominant contribution to everything you do here, or would this change totally on your plot?
I don't think all that much will change. Maybe Marcus can correct me. I mean, in the end, it's a question of optical depth. So here, I don't think, would it change?
You mean
the
what-
Waxman-Bahcall
The
calculation?
Waxman-Bahcall? I think there's some assumption about the number of charge pions that you produce.
Yes,
right? I
that's
mean,
right.
that-
So this
yeah.
factor here will be different, but
Right. So,
yeah.
Yeah, so in PP interaction, 2/3 of the pions will be charged. So you get actually more out of that compared to P gamma interactions. Okay, then yeah, I guess then we
Okay,
can continue with the next topic a
great.
little bit.
So I know
I think we have
we-
15 minutes.
Okay,
for the lunch
there
break.
is only one problem, which is that I've assumed we're gonna cover some of the next thing that such that you can do the exercises. But if need be, I can speak for a few minutes at the beginning of the exercises, okay? So here I'm gonna start giving an overview of the different possible sources. And so there was a question. And so I'll start by talking about active galactic nuclei. So active galactic nuclei are essentially galaxies which have a real excess emission to what we could attribute to any normal galaxy, and that's about a factor of 1,000 more than the light from all the stars. And therefore we know that there is an additional source of radiation. And we also know that that radiation comes from an extremely compact part of the source, and that we think that that is a supermassive black hole accreting matter. So we see, this is what, if we look at an optical spectrum of a normal galaxy, we have some emission lines from ionized hydrogen. But in an AGN, what we see is a lot more ionized gas, so much more prominent emission lines, and also very broad emission lines like this. And the broadening is inconsistent with being just because of temperature. That's inconsistent with having a sort of recombining hydrogen, and it has to come from bulk motion. So that's what we know. We know that there is bulk motion in a compact region and a lot of hot ionized gas. And we observe this behavior in about 1% of galaxies. And sometimes we observe these kind of dust stars as well, shrouding whatever is inside the central engine. So what is this engine? In fact, we have observations of the UV part of the spectrum of AGN, and we see something, it's not quite a black body, but okay, it can be approximated as a black body. And this is what we think is the accretion disk around the supermassive black hole, with emission peaking in the UV part of the spectrum. So I wanted to show you why we think this is a supermassive black hole and nothing else. So if we take a somewhat typical disk luminosity, so this is the luminosity we infer for this AGN, 10 to the 46 ergs per second. That's about 100 or 1,000 times, I forget exactly, the luminosity of the Milky Way. And we know that that emission comes from a region. So the emission is extremely variable in timescales of an hour. And so we know that in order that we're observing this emission, the region is very compact, because otherwise the emission that comes from the far side of the source and from the near side, they would wash out any intrinsic variability. So that gives us an upper limit to the size of the source, and it's basically this very subparsec. So it's 20 astronomical units. That's a really small size. The only thing that could be feeding this process is a supermassive black hole, and that could fit in this region. But I sort of want to illustrate that whatever it is, it has to be radiating close to its limit. So if we take the Eddington luminosity, so that's the balance of gravity and internal radiation pressure. So if luminosity becomes too high, the internal radiation pressure is very high, and eventually I'm pushing everything out. So I'm going to stop the accretion around in this disk. And so it's not exactly like a star where this is an absolute limit, but it's still a very important limit to respect. That the maximum luminosity cannot be higher than this Eddington upper limit. And so if we, this is normalized to, I forget what, but okay. The point is here that an object at least as massive as 10 to the 8 solar masses has to be invoked in order to explain the kind of luminosities we observe in typical AGN. So we think we're dealing with these supermassive black holes accreting matter. Now, in an AGN, those of you that read AGN literature, you will have seen that there are thousands of names, and everybody has a hard time to remember what is each one of them, because this is a lot of observers, they all observe something else, and there are all different types of classifications. But there is one scheme called the AGN Unification scheme that aims to explain all AGN in terms of few parameters. First of all, whether they have a jet or no jet. So this is a jet perpendicular to the accretion disk, and it's launched and observed in about 10% of AGN. Second, whether they have, what is our orientation? So if I'm an observer sitting here, I'm not gonna see the jet. I'm gonna see something which we call the blazar. If I'm an observer sitting here, I'm gonna see a beautiful jet. And this is what we call a radio galaxy, or what I called previously a jetted AGN. But if there is no jet, then we call these Seifert objects, and then we have Seifert type 1 or type 2 based on whether we're looking from this side or from this side. Okay, orientation again. Then because if we're sitting here, we can't see the disk. We see something to do with the dust surrounding the AGN. And finally, whether there is efficient accretion. So there seem to be some AGN which radiate close to the Eddington limit, and others that are more lazy somehow. They don't reach the Eddington limit. They are sub-Eddington. And so these are just a few pictures of AGN jets. And what I wanted just to say here is that certain AGN have jets which are, there was this point about accretion, and we think that this is related to the jet shape. So certain jets are very collimated and very powerful all the way until they hit, sufficient interstellar matter that they terminate, but they're still very energetic. Whereas there are these sort of weaker ones that end in a kind of uncollimated structure. Now, blazars are, maybe you remember here, when we have a jet in the AGN and we're looking into the jet, we see something that looks like a star. So we don't have a pretty picture of the jet. And we see, the only thing we see is spectacular variability in these, in the light curves. So there is no jet, there is no blazar, which is kind of quiet. They're all very variable in their emission. So we know something is happening in this engine. And okay, when we're looking into the jet, what we see is relativistically beamed emission. So here, these are just the usual special relativity. So when we're looking at a length at the rod with some length L in special relativity, we observe the contracted length and the time is dilated. But if we have a source with the same length, but it's emitting light, then things get complicated because we have the source catching up with its photons as it's moving relativistically. So we have the combination of the so in the length example, we have the combination of the length contraction and the Doppler effect, which gives us this beaming. So here, all I want to highlight is if we were to take, so for a typical blazar, the Lorentz factor can be 10 or 15. So if we look at this red line, which is 10, you see that if we're in the close to the if we're looking into the jet, we have a large Doppler factor, and then soon if we get out of the jet, we have a deboosting effect. So we have strong boosting headlight effect if we're looking into the blazar. And these are the relations then for time, energy, and lengths as measured in this case of beamed sources and luminosity. So note that, so for a jet with Lorentz factor 10, and we're looking into it with almost angle 0, the Doppler factor is 20. And so the observed luminosity is 20 to the 4th power larger than the true rest frame luminosity. And I'm mentioning all this is going to be part of the exercise that you're going to do later. And I realized that I forgot to tell you what angle to assume. So I think when I did the exercise myself, I assumed angle 0. Okay, so you can take what you want, but just be aware that there's some degeneracy. And yeah, so the point here is these are the brightest sources we detect in the universe. When I talk about brightest, I mean long-lived, not GRBs. But this is the reason that we have this huge boost in this relativistic beaming effect. So when we look at the gamma ray sky, all we see, except for this red here, is the galactic plane and galactic sources. Outside the galactic plane, all we see is blazars. Except for now, I should update this. There are maybe 3 GRBs. No, here, sorry. This is also true. So this is Fermi. So this extends out to 300 GeV. If we look with ground-based gamma ray telescopes, they can go up to higher energies, up to 10 TeV. Again, all we see is blazars, and there are 3 GRBs now also detected. So blazars are clearly the dominant extragalactic source of gamma rays, and that's why everybody is excited about them. Now, because of the beaming effects, remember the emission lines I showed before, we don't see these in at least half of the blazars. And that's because we're just seeing their jet. So the jet is blocking the host galaxy and the disk and everything. So all we see is some synchrotron emission here and some inverse Compton emission at higher energies. Now this doesn't have to, so this I have to explain because this is what you're going to work on, but I think it comes again. Okay, so in at least the fraction of blazars, I think I have another slide. Okay, just for the moment, remember this, that we have this very characteristic shape, 2 bumps, one typically in the optical that varies from blazar to blazar. Sometimes this can be all the way into the X-rays, and another bump in the gamma rays. Okay, and that's synchrotron emission for sure. And that there are many options, which I'm going to talk about in a moment. So, and I just wanted to highlight that depending on whether we can see the accretion disk or not, we call these blazars BLAC objects and flat spectrum radio quasars. So if we can see the accretion disk, then that means that the accretion disk is extremely close to it. It's very close to its Eddington limit, and this is one of these highly efficient accretors. And these are flat spectrum radio quasars. And one of the properties that they have is that this peak here is more prominent than this lower energy one here, which is not the case in these lower efficiency sources. Okay, yeah, so here this just summarizes what I said before, that this is thought to relate to efficient accretion. Yeah, okay, this is the final thing I want to say. So what we think is happening is there is a population of electrons in the jet. I'm not going to say anything about protons today. We'll talk all about this on Wednesday, because without protons, we're not going to get any neutrinos. But that's okay, because I think we're just building up. So we have at least a population of relativistic electrons in this jet. And what we think is that there's some kind of, it could be spherical region, and it's moving relativistically further away from the black hole in this jet. And so the electrons that radiate the most in synchrotron emission are the ones with the highest Lorentz factor, gamma B, and afterwards there might be additional electrons with higher energies, but these have, what we think happens in most sources is that there are some electrons that do not have time to cool efficiently before new ones are injected. So these are the low energy ones. The high energy ones lose energy faster. So typically we think that there is a spectrum with a spectral break. That doesn't matter so much, but it's just a parameter that goes into here. So the emission that we see, the synchrotron emission, gives us a handle on the magnetic field strength in the source and on the dominant electron Lorentz factor, this gamma B, and the Doppler factor of the source. Now, if these electrons are working twice, that means, first of all, they produce the synchrotron emission, and then they go and inverse Compton upscatter the photons that they just produce. So we have low energy photons produced from synchrotron emission. This is here. And then the electrons upscatter via inverse Compton processes the photons in this medium. Then we get the second peak. And this is the inverse Compton peak. And this is just the standard formula for where the peak of the inverse Compton emission is in the case of in the Thomson regime, which is the only one we're going to consider today. So we have, you see that we have two expressions which can help us constrain the break of the Lorentz factor of the electrons. And you're going to use this in your exercise. And I just want to say here that this is not the only possibility. I already mentioned there's this other population where this peak, where the gamma rays are, is generally too high to be compatible with coming from this one electron population. But we know that in these sources, there are a lot of photon fields surrounding the accretion disk because there are gas clouds. And we see these emission lines. And we know that there are gas clouds in rapid motion that are re-emitting the light from the accretion disk. And so we think that much more likely this inverse Compton emission in some sources comes from these external photon fields. In addition, the gamma rays could be coming from pion decays. So we're going to talk about that on Wednesday. I'm going to stop here, and just to give you, since we made it, I think just time to stop. What I'm going to ask you to do is to try to fit some Blazar data and see whether that source is consistent with this model, which is synchrotron and inverse Compton emission from the same electron. So we call this a synchrotron self-Compton emission. Okay, so I'll stop here.
Thank you, Foteini. So yeah, I guess so. The exercises will be today at 3:30, and maybe we can then set up your screen, and then you maybe introduce the
Yes.
exercises, and then we can do this in groups.
Yeah. Okay.
Okay.
Yeah.
Are there any questions? Yeah.
Hello. So I have questions. What is the region of jet? What is the
Please
region of?
speak a bit louder.
Okay. What is the region of jet in case of AGN? Some AGN has jet, but some don't have jet. So what is the reason behind it?
Yeah, that's a great question. I think nobody knows. But the fact is, no, the fact is that we see it sometimes and we don't other times. So we don't know exactly what the initial conditions have to be. But it's related maybe to the spin of the black hole, maybe to having the correct magnetic field so as to launch the jet. Many unsolved questions in astrophysics, I would say.
Any other questions? Are there any questions on Zoom, Maurizio? Do you see any?
No, but if you have more questions that come to your minds later, there's a discussion session afterwards.
Right.
Okay.
Okay, then I think we should break now for lunch. Let's thank Foteini again.